Good afternoon, ladies and gentlemen. I would also like to welcome you to my presentation for my paper approach to an iteratively coupled thermal and aerodynamic design process for a production car. The written paper is composed by two parts. The second part is a broad validation base for a production car, and the first part, which I will present today, is the simulation process. So this is the outline of my talk. I will start with a motivation for an aerothermal design process, or in other words, is this a right problem? Then I will explain the aerodynamic simulation, and afterwards the thermal simulation, and I will show you the models I will consider for my paper, and afterwards I will show you how can I couple these two simulations for the considered models. I will show you some results for one of the models, and I will conclude with an outlook and of course a conclusion. So the motivation for a coupled design processes. Here we can see the distribution of the different resistance onto consumption. We can see that the aerodynamics is the largest part if you're considering battery electric vehicle. And this is only for a European driving cycle where the average speed is really low. So if you're considering a customer driving cycle, the aerodynamic resistance grows to over 50% onto consumption. Second, if you're considering battery electric vehicles or plug-in hybrid vehicles, we have a lot of new components which we have to fit in a car and which have specific cooling requirements. For example, I'm having here an electronic motor, maybe some kind of range extender, of course a driving battery and some other electronic parts. And all these parts have specific cooling requirements and will change the packaging of the car completely, so that we cannot rely on our experience. And third, the interaction between aerodynamics and cooling is mostly a goal conflict. For example, we're having here the underbody of an Audi A3, and the yellow arrows show us where we have a goal conflict. For example, here, where is the exhaust system, we cannot cover the underbody in order to have a smooth underbody and the lower drag resistance. Second, the wheels, the brakes have to be cooled, and also the car the flow through the car is also a goal conflict. So we need a coupled aerodynamic design process if we want to consider all these problems. So if you look on a typical design process of a production car, we start basically 4.5 years before the start of production, marked here, with the aerodynamic development, which is composed by, of course, CFD simulations, and in the beginning 1 to 4 wind tunnel models, and afterwards 1-to-1 wind tunnel simulations. On the other hand, the thermal development is mostly completely decoupled, and first with the real physical prototype we can experience the real interaction between cooling and aerodynamics. Has all the assumptions we have made for the coolings, has they been right or not? And this gives us only 10 months to approve the cooling if wrong assumptions has been made. So this is a really short time period, and mostly the aerodynamics is getting worse. So with the aerothermal design process, we could gain 2 years in development time, and this is where my project AeroOpt is approaching. So for the aerodynamic simulation, I am considering 3 types of temperature modeling. The first one is called the scalar DES. As turbulence modeling, we have the detached eddy simulation model with the Spalart-Almaraz runs model. This one is an incompressible solver, and it is extended by a scalar passive temperature transport equation. So this means we have no retroactivity from the temperature field onto the flow field. The second one is called the buoyant DES. This is also an incompressible solver. It's basically the scalar DES solver, but now we're considering buoyancy effects in the momentum equation. Here the density is not constant anymore, but it is it is dependent onto the temperature. And the last approach, which is the physically most correct approach, is a compressible solver. We're also using the DES turbulence model, but we are solving the conservation equation for enthalpy and of course equation of state for our ideal gas. The thermal simulation, this is an in-house thermal FEM solver. We're solving on a tetra volume mesh, and here we are considering all three types of temperature transportation, which is the radiation is considered as a diffusive gray body radiation. The convection is calculated like this, and here we can see this is the heat transfer coefficient and the temperature of the near wall temperature, which is the temperature of the first cell, and this is where the CFD simulations comes into the model. And the conduction inside of the model is simulated with the law of heat conduction, Fourier's law. The models I'm considering is my validation model. It's a small block test case. You can see it here. It's made out of solid aluminum, but in the inside I can heat it up with 4 electric cartridge heaters. Like this I can get a maximum temperature of about 130 degrees, and the simulation target is to simulate the cooling curves. How long does it take if I have the block in the wind tunnel, and I switch off the heating, how long does it take to cool the block down? And of course the limit temperatures, what is the maximum temperature I can get if I have convective cooling. The second model is an Audi A7, and here in the rear axle carrier I have assembled a fictitious electric motor. This one, you can see it here, it's also made out of solid aluminum, and I can also heat it up with 2 cartridge heaters to define temperature. And here also the target simulations are cooling curves and limit temperature. So how can I couple the aerodynamic and the thermal simulation? This one is not easily done. If I compare the simulation time for the CFD simulation, normally we simulate 2 seconds of physical time. For the thermal simulation, I would like to simulate like up to an hour of physical time. So you can see that this is quite a huge difference. For the flow simulation, I have 2.3 million cells for the cube test case and 100 million cells for the car test case. And on the thermal simulation, I have only like 60,000, 200,000 cells, volume cells, and some surface cells for the radiation. But the thermal simulation is done in 1 hour, 2 hours on a personal computer, and the flow simulation takes up to 6 days on the cluster. So we can easily see that if I would like to couple these 2 simulations interactively, I would have to simulate up to an hour within the flow simulation. So if I simulate 2 seconds and this is like 6 days, it's clear I cannot couple these 2 simulations interactively. So because of the huge simulation time. So I've come around with a different coupled process. I start with an initial CFD simulation. I have to make a first guess for the surface temperature, and I get an initial guess for the heat transfer coefficient on the surface. Then I start my first thermal simulation. I have the input from the CFD simulation, which is the surface temperature, the heat transfer coefficient, and the temperature of the first cell. And now I get a distribution of the surface temperature for my next CFD simulation. I update the surface temperature and get a new heat transfer coefficient. And now I can simulate in a last thermal simulation my cooling curves or my limit temperature. The assumption under this process is that the heat transfer coefficient is mainly dependent on the flow field around the cube and not on the excuse me, not on the surface temperature. So to validate this process, I am comparing the heat transfer coefficient on the cube after the first and after the third CFD simulation, and we can see here that the integral values vary by 0.2%, and also the distribution on the surface, which you can see here, is barely visible. So the coupling process like this is enough, and I need no further coupling. Now I would like to simulate cooling curve and compare them with wind tunnel results. You can see here the solid line is the experimental curve out of the wind tunnel at the Technical University in Munich, and the dotted line is the cooling curve from the coupling process with the scalar DES model. And we can see here in the end, in the beginning, the temperature decrease is a little bit overestimated, but in the end the curves are fit quite well. If we're now comparing this result with the buoyant DES solver, you can see that for the buoyant DES solver, the temperature decrease in the beginning is a little bit better, but in the end, the temperature is higher than in the experiment. So what is happening here is that if I hand over the near wall temperature, which is the temperature of the first cell of the CFD simulation, to the thermal solver, this will be my limit temperature. I cannot cool down more than this temperature. So I have to change the reference temperature for the heat transfer coefficient, and I can easily calculate the physical heat transfer coefficient by the definition, and now I get a quite better result for the two cooling curves. You can see that the temperature decrease is still a little bit overestimated. This comes out of the CFD simulation where the heat transfer coefficient is overestimated. And the last result is comparison. Comparison with the compressible solver. We can see here that the buoyant solver and the compressible solver, the results are quite the same. So it looks like it's the same curve, but these are different curves. But the result is that I can gain no more no effect through the compressible solver. So these results are basically the same. So to conclude my talk, I have explained the need for a coupled aerothermal design process, but the fully interactively coupled simulation is unfeasible due to the huge simulation time. I have set up the iteratively coupled simulation process, and I have shown you some cooling curves for the block test case. And there's no advantage for the compressible solver. So the next task would be to applicate this simulation process onto the productive car, and of course to improve the wall treatment and the result for the heat transfer coefficient out of the CFD simulation. Thank you very much.